The desert had a way of swallowing things. Old roads vanished under drifting sand. Buildings crumbled quietly into dust. And sometimes entire secrets disappeared with them. In the late 1960s, in a remote stretch of desert far from any city lights, a small research complex appeared almost overnight. There were no signs on the road, no mention in scientific journals. Even the maps printed that year showed nothing but empty land. Yet inside those concrete walls, scientists were attempting something astonishing. They were trying to build a sun, not metaphorically, not in theory, a real one. Not large enough to light a planet, of course, but powerful enough to recreate the same nuclear fire that burns at the center of our solar system. The lab was known only by a short internal code, Helios Facility 3. Almost no one outside the project knew it existed, and for decades, almost no one remembered it at all. At the heart of the project was a problem that had fascinated physicists for generations. Stars produce energy through nuclear fusion. Hydrogen atoms collide under extreme heat and pressure, merging into helium and releasing enormous amounts of energy. It's the most powerful energy source known in the universe. If humanity could control that reaction on Earth, it would mean nearly limitless energy. No fossil fuels, no massive radioactive waste, just the same process that powers the stars. But recreating a star is easier said than done. Inside a star, gravity provides the crushing pressure needed to force atoms together. The core of our sun reaches temperatures of about 15 million degrees Celsius. On Earth, there is no gravity strong enough to replicate that environment. So scientists needed another way. Helios Facility 3 was built to explore one of the most extreme solutions ever attempted. Instead of squeezing atoms together slowly, the researchers would slam them together violently. Their plan involved creating tiny bursts of fusion using pulses of unimaginable energy. At the center of the laboratory sat a massive experimental chamber. It looked like a metal sphere the size of a small room, surrounded by thick cables, reinforced shielding, and towers of electrical equipment. Inside that sphere, they would place a tiny pellet made of fusion fuel. The pellet itself was barely larger than a grain of pepper. Then came the real challenge. To ignite fusion, the pellet needed to be struck from all directions at the same time by enormous energy pulses. The impact would compress the fuel so rapidly and intensely that for a fraction of a second, conditions inside the pellet would resemble the core of a star. In other words, a synthetic sun. But generating that kind of power required machines that had never existed before. The facility was equipped with some of the most powerful pulsed energy systems ever constructed. Banks of capacitors lined entire hallways, storing massive electrical charges. When triggered, they would release their energy in a single blinding flash. The first test took months to prepare. Scientists calibrated sensors capable of measuring events lasting only billionths of a second. Cameras were installed behind layers of protective shielding. Engineers triple-checked every system. When the day finally arrived, the team gathered in a control room, separated from the chamber by thick, reinforced walls. At the center console sat a single switch. When it was thrown, the capacitors discharged instantly. For a moment, the entire facility shook. Inside the chamber, the energy pulse struck the tiny fuel pellet. Sensors recorded a spike of temperature far beyond anything previously created in a laboratory. For less than a millionth of a second, the pellet reached temperatures hotter than the center of the sun. Fusion reactions occurred. A synthetic sun had been born, and then it vanished just as quickly. The burst lasted such a short time that the total energy released barely powered a light bulb. But scientifically, it proved something remarkable. Humanity could create stellar conditions on Earth. The experiment opened the door to an entirely new kind of energy technology. Over the following years, the team refined the system. Energy pulses became stronger. Diagnostics became more precise. Each experiment pushed the limits a little further, but the project remained deeply secretive. Part of the reason was simple. The technology had enormous military implications. The same physics used to ignite tiny fusion pellets could also influence the design of advanced nuclear weapons. Governments funding the research were careful to keep most of the details hidden from public view. So the Helios facility operated quietly, publishing almost nothing about its work. Outside the desert compound, the world had no idea that miniature stars were being created behind those walls. Yet the experiments weren't without problems. The extreme forces involved often destroyed equipment. Diagnostic instruments melted or shattered under the intense bursts of radiation. Even the chamber itself needed constant repair. And despite years of effort, one key milestone remained out of reach. For fusion power to be useful, the reaction must produce more energy than it consumes. That moment is called ignition. The Helios team could trigger fusion, but they could not yet sustain it long enough to produce net energy. By the mid-1970s, funding began to shift toward larger and more advanced research centers. New facilities promised stronger lasers, more powerful compression systems, and better containment methods. Helios Facility 3 slowly faded from importance. Experiments became less frequent. Some of the original researchers moved to other programs, others retired. Eventually, the complex was quietly shut down. The buildings remained in the desert, abandoned but still standing. For years, the place attracted almost no attention. The records were buried in classified archives, and the facility itself appeared on few public maps. The synthetic suns created there had been so brief that the world never noticed them. Any research experienced a revival. Scientists began revisiting old experimental data. Among the archived documents were reports from the forgotten Helios experiments. The numbers surprised many researchers. Despite the primitive technology of the time, the Helios team had achieved compression levels that rivaled much newer systems. Their methods, once considered outdated, suddenly seemed ahead of their time. Some modern fusion experiments even rediscovered techniques first tested inside that dusty desert chamber. Today, laboratories around the world are closer than ever to achieving sustained fusion power. Massive laser facilities fire beams containing more energy than entire cities consume in an instant. And when those beams strike their targets, they recreate conditions found only in stars. Each experiment produces another tiny artificial sun. For a brief moment, temperatures soar into the millions of degrees. Atomic nuclei fuse together, energy bursts outward, then the reaction fades. But one day, perhaps soon, the reaction won't fade. The synthetic sun will keep burning. When that happens, it could transform civilization forever. And when historians look back at the long journey toward fusion power, they may rediscover the quiet desert laboratory where some of the first artificial stars were born, a place almost forgotten by time. Helios Facility 3.